carried out and then properly interpreted. And you might want to highlight the relevant outcome, the relevant p-value in that normality test. The reason why that's useful gets back to a question that I think Robert asked yesterday about getting the wrong interpretation, but then continuing to do the right thing. If for some reason you've read the wrong number of the output, so let me go down to the normality test output. Let's say you had a moment of panic and you read this particular significance value, or you even read that statistic. If you've highlighted the right thing, I know what it is you think you've read, and then I can factor that into the marking. Whereas if you just tell me that the p-value's bigger than 0.05 or less than 0.05, I'm left to guess that you've looked at the right thing and read it wrong or whatever. It's much better for both of us if you make those highlights. Then we get to the statistical tests themselves. So, the question came up yesterday, what are they going to cover? They're going to cover something on that page and not more than that. I'll not be asking questions to require tests that we haven't covered. So it'll be one of those tests. And what I want you to do is explain to me why that's the relevant test. So again, if, for example, it should be a paired t-test, but for some reason you've panicked and you think it's independent data, well, there's the opportunity to tell me why you thought it was independent data. And if it's not sensible, then no marks be awarded for that. Whereas if it is a reasonable thing, then maybe I can give you some credit. And again, once you've justified the test, do the test, do it properly on the right data, highlight the right significance values, or in the correlation cases, the significance and the strength of the correlation, and then interpret the test properly. And finally, just always have a little section at the end, like I have done in my examples, which actually goes back to the original question and shows that you're able to answer the question based on the test results. Does that make sense? Any questions on that? Silence in the chat box. Okay. No, it didn't make sense, or no questions? Sorry, Robert, I think you mean no questions. I'm teasing. Good, that's fine. The voice of two will do for the voice of the class. Right, what I now want to get into are ANOVAs. So here, because I want to show you three things today: the ANOVA, the regression, sorry, the ANOVA correlation, and then the regression. So I've got one data set here, which is a nonsense problem. It's to do with the depth of water in a particular measurement, going from 0 to 30 feet under the water to 40 to 70 to 80 to 100. And these are iron level measurements at different water depths. The crucial thing is that there's three groups. And so because there's three groups, we would expect to do an ANOVA, more than two groups, all right? Let's start with a box plot. Legacy dialogues, box plot, simple. And again, we want to do this. This is a summary for groups of cases. This has come up in email a couple of times. It's separate cases when they're in separate columns that you're trying to visualize, that you're trying to do the box plot for. Whereas if it's all in one column with another column next to it that defines the groups, then it's groups of cases. So here we have iron measurements, the thing we want to measure. Obviously, I was working through the data last night, so there's a bit of legacy there for the next part of this tutorial. We want to measure the iron, and we want to have the category based on the grouping variable. And what this is going to show is, if it shows anything at all. Where's my, okay, slow machine. I had a panic moment there. I thought something else was going to go wrong. We can see here a very simple box plot. These three values, these three data ranges are really quite different. Obviously, the iron measurements going up as you go further down. That might be something to do with iron sinking, I imagine. The next thing you would do is the normality plot. Now, I haven't introduced the group test for the non-parametric equivalent of an ANOVA. Just for reference, and a couple of people have asked me, it's a Kruskal-Wallis. That's the name of the test. It's a non-parametric. If we were still in class, if we were still active in the building, I probably would have added this into the materials. But you know, given where we are, I decided not to. Let's look at the normality tests. We check that the box is ticked in the right place. Untick the stem and leaf diagram. Run the system here, and what we'll see in a moment, I hope. Yep, is that I've done it on the wrong data. Here's one I tried earlier. That's a Blue Peter reference for anybody that knows that. That's for my next work example. That's the alternate data set, because my brain is clearly in last night. Let's do that again properly. And that just shows you how quickly it is to redo a normality test. That's the reason I did it, honestly. So you can see the next data example's got 5 groups. And you can see that all of these are normally distributed. Now, this p-value here is an indicator of how normally distributed the data is. So that first group is pretty perfect. This one is not very normally distributed, but still sufficiently normally distributed. And if we go back to the box plot that I did when we started, you can see that this one looks very normal. This one looks less normal. So there's clues in the data as to whether you've processed the right thing, whether you've analyzed the right thing. So given all the data is normal, we can do our ANOVA. And of course, because we haven't done the Kruskal-Wallis, then do the ANOVA anyway, normal data or not. The ANOVA itself is very straightforward. It's, again, in our compare means option. It's the bottom list. I need to watch the right screen when I'm doing this. I'll make sure I've got the right data. A useful tip for the exam is that if you stretch the box out, you can see the full width of the name. That sounds obvious, I suppose, when I say it, but some of the Creative Nation names are quite long, and so it's helpful to stretch that box out. That's what we want to do the test on. This is our water depth. That's the grouping variable. And remember, we do our post hoc test, which is the Tukey test. So we hit continue on here, and what we'll get is, because the data is very far apart, you can see it in the box plot, you can see the data is far apart, we get a really nice, clean example of a difference with an ANOVA. So the significance value we're interested in here is clearly dead on 0. So there's big differences in that data, and that's not a surprise when you look at the data. What the post hoc test does is do a series of pairwise comparisons within the ANOVA. So 30 feet is compared to 40 to 70, and is also compared to 80 to 100. And the remaining test, the 40 to 70, is compared to 80 to 100 there. So there's 3 values that matter: this one, and this one. The others are just duplicates of that, because it does every test in every direction. And so what we can see here is that, helpfully in this example, everything is different. All right. Is all of that okay so far? ANOVA is a very straightforward test, and it's one of the easiest ones to identify because it's only done when there's more than two groups. The only tricky bit is getting the interpretation right from the post hoc test. So with that in mind, I added in more data to make this not quite so trivial. And I'll show you that data now. So as in every answer that I'm looking for, we're going to start with our box plot here. Groups of cases again. But instead of using that first column of data, I want to use the second column of data, which has not 3 categories, but 5. And you can see what I've done there. I've introduced a 4th and a 5th level that are clearly blurring the difference between the groups. So this one here is obviously overlapping with group 3, and group 5 is so wide that it's overlapping both 4 and 2. So now when we do our normality tests, using the description here, I'm going to put the other group labels in. And we're going to get 5 normality tests done now. And you can see that all the data is normally distributed. Because of course to do a not normal test would require a test that we haven't done if the data wasn't normally distributed. And it probably took longer to get the shape of the data right than it did to do the question. So we can do our ANOVA, which we'll do. Again, it's exactly the same place. We have to put the 5-way grouping in, otherwise we won't get the right answer. We have to put the right measurements in. I hope this is going to work. So this is our new set of results. As you can see, it's a little bit more complicated now. There's a significance value of 0, so there's definitely some difference in the data. And all that tells you is that at least one data group is different from at least one other. It doesn't tell you any more than that. Of the 5, 2 of them can be different, the other 3 could be the same. We can't tell based on a single number, hence the post hoc. So what we see is that for 0 to 30 feet, that group of data is significantly different to all other data, all 4 other groups, because all of these values are below 0.05. The 40 to 70 group is of course different to 0 to 30, because we've just seen that. It's different to 80 to 100, it's different to 110 to 150, but it is not different to the 150 to 200. And if we go back to the box plot, where's the box plot gone? I'm struggling with lag here. The box plot is there. Stay still. You can see that this group is not different to that group. So it's showing you the overlap. And if we continue working our way through, we see that 80 to 100 is of course different to the previous 2. It's not different to 110 to 150, and there's a reasonable amount of overlap there, but it is different to the final group. The 150 has actually got 2 non-zero p-values in it, one of which is still significantly different, the other one not, and likewise for 150 to 200. Now, where this gets a little bit more complex is if you're asked to determine whether any one depth has got less iron than the other, you can do that, because this one is significantly lower than all of the others. If you were to be asking which depth level had the most iron measured in it, it's clearly this one, but this value is not significantly different to that one. So you might comment that one of them is bigger, larger, at a higher level, but not significantly so to the others. And that's really the level of interpretation I'm looking for there. Seems straightforward? Okay, any questions on that? That's the end of my ANOVA coverage. There really isn't much more to it than that. Okay. Let's go now on to our correlation questions. So here we have a data set, and ignore the third column again. That's going to be used to illustrate a different issue. Here we have a data set that relates, or that has in it, for 20 different players, the amount of money they spend within a game versus the number of hours played per week on average. And so the question might be, is the spend in games related to the number of hours per week? So to do that, we're going to do a correlation. All right. Correlation is very easy to do, but we'll start with a scatter plot. The scatter plot has got, always stick with the simple scatter plots. It's got two axes. On occasion, I get questions, which is the X and which is the Y. My little way to remember that is just to remind you that X is a cross, because it's a cross. So X goes across the bottom. So what we want to do is we'll put the in-game spend on the Y-axis, the vertical axis, and the hours played on the X-axis. And we'll get a nice tidy plot in a moment, which shows that there is at least some broad trend. It starts off fairly tight, but then starts to spread out. People here like to spend a lot of money in their games, and these people like to spend very little in their games. So that looks like there's probably a positive correlation. But let's check and see if it's significant or not. So we go to correlate, and the first option is bivariate. It just means there's two variables, which is all we're looking at here. The only decision that you need to make is whether it's a Pearson's or a Spearman's correlation. If the data is measures, so if it's shown as rulers, then it's a Pearson's. If the data looks like an ordinal or a nominal, then you would use a Spearman's, but the interpretation, the process is exactly the same. You just tick a different box. And I'll remind in the notes, it's covered how to do one correlation or the other. Let me find it. Pearson's correlation bivariate. Okay, it's a different menuing system, but it's you put the two values in, you leave Pearson's ticked. It shows you how to interpret. What we're looking for are two values, one of which is the significance, the other is the correlation strength itself. So the way that you interpret those correlation strengths is if it's nearer to 1, plus or minus 1, then the correlation's stronger. So we'll just explore that by playing with the data a little bit. Let's do our correlation of the in-game spend and the hours played per week. Pearson's correlation. It helpfully flags significant correlations for you. So it even tells you correlation is significant at the 5% level. And that's because it's this value here. 0.021. It's a moderate correlation because you can see it's not particularly strong. That's not close to 1. It's about half a value. If we were to go back into the data and make a small change, let me see. This one here is a very low value for a large number of hours per week. I'll just drop this down to a smaller value as well. If we redo the correlation, I'll redo the plot, scatter plot. You can see that what we have now is a slightly tighter fit. I've removed this data point. I've removed one of the data points from down here. I haven't removed this one yet, but if we do our correlation again, we see that the significance is similar, and the strength of the correlation has increased. So it's still positive. It's now more significant than it was, and it's gone up from 0.5 to nearly 0.75. And obviously, if I were to remove or change this data point here and put it in this region, it would tighten and tighten and tighten, and then the correlation would get more and more strong. Okay. The alternate data set here is generated just through a random number generator. So let's compare those two. Let's get rid of this spend pattern and put the randomly generated spend pattern in. And what you'll see when I do this correlation, or this scatter plot, sorry. What have I done? That's the same data, isn't it? Is that it's now, sorry, it's not randomly generated. This was the one that I forced to be very good, and I'll show you why. This data set is obviously much tighter. I have removed those outliers, and now when I do the correlation with the alternate rather than the actual spend, you'll see that this has gone up even more. So it's now almost 0.9. It's almost perfectly correlated. Okay, let's go back to that original plot. I'll redo it again because it's easier than finding it. This original plot. We want to know if you can make a prediction. Imagine you would want to know if somebody was spending 2.5 hours a week playing, could you predict how much they would spend? So this is where the linear regression comes in. All the linear regression does is fit a line through the data. So we can do that. We can go to analyze and we can go to regression, linear. The dependent variable is the prediction we're trying to make. This is what we're seeking to predict. So our speculation is that spend depends on hours played per week. So the hours played per week goes across the x-axis. This is the y-axis, because the linear regression does this formula. where our Y value, which in this case is going to be the in-game spend, the Y value is dependent on the X value according to two numbers, one of which is a constant, which is where, and I'll show you this now, the constant is where if you had a zero line, the line would kind of intersect, because that's if anybody plays the game at all, they would in this case spend £5, and then you have that's the C, and then the M is the slope of this line, this gradient. So we can see here that we have our constant of 3.2 and our hours played of 2.4, and that this prediction is a pretty good fit. Okay, we'll go to my notes here, and what you're looking for when you do the prediction, it allows a prediction of Y, that vertical axis, based on X, the horizontal axis. One is dependent on the other. I've got my slide the wrong way around. It's not the best time to be changing this, but I'll sort that out. Y goes in the dependent box. I've got my narrative here, right? That's right. This says, that shows how easy it is to make mistakes in this stuff. There we go. Typo fixed. We want to know the R² value, which is how good the fit is, and also the constant and the gradient. So what you can do in SPSS is, where's my output window gone? This one. You can click on the line. If you double click on the chart, it opens up the chart editor, which is here. And I can fit a line with this option. It says add fit line total. I get to fit, it fits a linear line by default. Now, a curious thing is I press close here, and I get an R² value of about 0.5, which is okay. It needs to be higher than 0.5 to fit, and you end up with your equation. So Y equals 3 and a bit, 3.2 plus 2.5 times X. So if we calculate that out, we end up with a value roughly predicting this line. So you can add that up. 2.5 times 2.5 is, somebody with a calculator to hand. You with a calculator to hand. Thank you. 6.25, and then you add 3.21 onto 6.25, and we're into about 9.5, which is pretty consistent with where that line fits. Unfortunately, the plot is directly on where I want to be, but you get an answer here that's about 9.5. Thank you, Cecilia. So you can use the line to then make a prediction. We close that down. If I were to use the other data set, what you'll see is if I redo the regression, but with the other data set, the alt that's a slightly better fit, we end up now with a much stronger fit. The R² value is much higher because the line is going to be a better fit, and we end up with a slightly different model here, where our constant is 3. So even if you play the game at all, you'll spend £3, and then the gradient of the line is around 3 as well. If we redo the plot on that, you'll see, and again, you may prefer just to work this out from the graph rather than from the regression. Either way is absolutely fine. We'll put the alt in. I don't know why I needed a calculator to work out 2.5 times 2.5. It's not hard. It's 5 plus 1.5, 1.25. Anyway. If we now double click on this, I'm trying to think about two things at once. We fit a line. We go for the linear regression, and we get again a slightly steeper line this time. The R value is better, so it's a better fit. And here we have the number of the amount of money spent is roughly 3 plus 2.5 times 3, which takes you into around about 11. And it's more because we changed the data to make the line slightly steeper. And that is correlation and linear regression. And if I just quickly show you are these the right answers? Yes. You know, the sorts of, this is the mock answers, which we'll go through next week, but I just wanted to show you. So question 4, we're on question 4 yet, no, question 4, had that type box plot, sorry, scatter plot. You can see that there's a strong positive correlation. It's very significant. This is a useful table. You don't need to repeat this in your answers, but it's a good thing to have in hand, and I will actually add this in to this slide deck. I'll just make a note of that now. I'll tidy that up and upload those slides. That's a useful thing to remember because it shows you whether it's weak and positive, moderate and positive, strong and positive. Here's our regression. In this case, it's done through the coefficients, but there's also the plot there, which gives you the equation. It's up to you whether you want to use it or not. For the R squared value to be, for the regression to be meaningful, it's got to be, you know, greater than 0.5. Below that, and it's not a prediction that's telling you very much. Yes, it still gives you a prediction, but it's not very accurate. So that's how you would answer that final question. It gives you this this equation set here. There's the constant. There's the gradient multiplied by x, y equals all of that. So I think there we go. Any questions on that? Or indeed any other questions? So this morning we had no technical problems, which is why, and there's a slightly shorter pair of examples as well. So I've shown you how to do the ANOVA, which I think is straightforward. Doing the correlation, this part of it I think is really easy. You just go into the correlation option on SPSS and you get the plot. The regression is a little bit more tricky, not least because there's two ways of doing it. You can either do it through the curve, through the line fit here, or or indeed through SPSS, and you know, it gives you the same things. Questions, please. Or have I missed anything? Anything you want me to go over? And Okay, so my plan for Wednesday then next week, I'll arrange the time. It'll be, yeah. So you've just anticipated what I was going to say, Lee. When we go over the mock exam, what I'll do is I'll walk you through the construction of these answers. But let's just, while we've been talking about the ANOVA, and conveniently question 1 talks about the ANOVA. The question says, which region out of these 3 regions, East of England, Northwest, and the West Midlands, has the largest change in employment? So we know it's an ANOVA because it's 3 regions. So going back to my little aid memoir, there I've just justified the statistical test. You can use the wide or the long. We'll talk about this in more detail next week, but that then selects out the 3 groups that you want. So nation region 1, which is the east of England, nation region 4, which is the west, northwest, and nation region 10, which is West Midlands. You do the normality test on those, like we just did a few minutes ago, and you get your 3 p-values done. Now, obviously, in this answer, I did the normality test before I did the plots. You can do the plots before the normality test. There's no running order to this, to whether you do the normality before the plots or the plots before the normality. You do the box plots, as we've just shown you, so that's the grouped cases. You can see that there's good overlap in the data, etc., and some sort of indicative narrative there. Comment on those descriptors. Again, we'll go through that next week. You can see the post hoc test, and after this morning, you should be able to tell that one of those is significantly different. The other 2 values are not. I've highlighted in red because I had the time that one was significant. You're under more time pressure potentially, so I wouldn't worry about highlighting the differences. And then there's our interpretation, and finally there's the statement that answers the question. Northwest has the greatest change in employment. It's not significantly different to the West Midlands, and so no one region is different to the other, which is exactly the same pattern as happened in our iron measurements data, where we had one that was higher, but not significantly so. Almost as if I'd primed this example to sit quite neatly with the example in the exam, where one is higher, but not significantly so. Do you think, as a class, that if I walk, having gone through all of the tests, just to remind you how they work, if we then go through the mock exam, can you think of anything else that I would need to do to help prepare you? Nor can I, Josh and Rachel. I can't think of anything either. I know that some students have emailed me separately, and that's absolutely fine. I'll try and answer questions by email as well. In fact, in 2 cases, I didn't read them in time, and then both students had answered their own questions about half an hour later, which is always nice. Are you generally happier than you were at the beginning of this week? Happier being a relative statement, of course. Anybody unhappy and willing to say so? A moderated answer, Michael. Good. Well, if anybody can think of anything else that I can offer, then do let me know. I'm open to ideas. But I think from this you kind of getting the overall. It can be both Wednesday and Thursday next week, Lee. I'm thinking that within a two. Let me just check my calendar. Calendar. Yeah, I've not got on top of my emails, as you can see. It's still a crazy thing. I probably need to start around 9 o'clock, but I can run on till 11 on Wednesday, I think, and then Thursday I've got as an available slot. So my plan is to spend probably 9 to 11 on Wednesday, going through the exam, and then have Thursday. I'll be here, and it's kind of an optional thing for you to drop in and ask questions. That's probably the best way to do it. That makes sense? And obviously, if there's a need, I know week 14 is it's labelled revision week. Week 15 is labelled your exam week. Just because it's revision week and exam week doesn't mean I'm not answering questions. The exam is on that last day in week 15, so we've still got 3 weeks after this one to deal with any potential issues, which I think is plenty of time. That's kind of why I did these classes after Easter as well, because if I'd have pushed them through beforehand, then the memory decay takes over. It's much better to do it nearer the time, I think. So I gave you a couple of weeks to work through it, and then that allows you to see where the gaps are, and then we can run through everything again in advance. And if there's a general sense that you want me to do another quick recap of every single test in week 15, maybe on the Monday before the exam, then I can do that. I don't particularly want to return to the questions at that stage, the exam type questions. But if you want me to run a session just running over how to do every test and how to interpret every test, then yeah, that I can do. On Monday the 4th or something, just as a reminder. And that was a little finance email popping up there, if you noticed. Can I do anything else today? I know that Bongo timed out yesterday because of the kerfuffle in the morning, but of course the time was set up to cut out. Did anybody have any questions? I answered Alistair's question by email on the university grading system, which I hope was sufficient. I noticed I missed out the value you get for an F, but the total value for an F is a 0, which is not worth writing down. It's quite hard to get an F in this exam, I think. If you have a look at this slide, if you're good at doing plots and you can do normality tests, and at least point in the right direction, that would take you away from an F if you did that in most questions. I'm going to stay here for another 5 or 10 minutes. Should any questions come to mind, I didn't want to particularly cover anything else today, and I'll upload. So I thought this was quite a helpful thing to add into the slide deck, and I'll just tidy up that new slide I added in here. And I'll upload those right now. Was the resolution okay for the Bongo system? You can read the documents and so on. Good. I think it's not a bad system. As I say, I'm not sure what was wrong yesterday. I tested it beforehand. It was fine. Do it live, it doesn't work. And all I did was reset my machine, and hey presto, everything worked. All right. Well, I'm not going to keep you longer than I need to. So Wednesday, 9 a.m. to 11 a.m. For the exam walkthrough. That's my proposal for next week. 9 a.m. to 11 a.m. for the exam walkthrough, and then Thursday from 10 a.m. for other issues. So I think, given the silence in the group, I think it's probably time to sign off then, until Wednesday, 9 o'clock. Yeah, bye. I'm glad this morning worked better. All right, and I'll speak to you next week, Wednesday, where I'll drive through the exam myself and make all of those runtime errors under pressure. All right. One more thing. This lecture, if you want to call it that, has been recorded. I don't know where the recording goes, but I'll try and figure that out and circulate something. All right. Bye.